By now, you have explored both in this video and with your facilitators the first two guiding principles for the development of the Common Core state standards, and the shifts to instruction these principles require. We now turn to the third and final guiding principle for the development of the standards, rigor. Rigor refers to what happens in the classroom, and is about more than just what is taught and what the standards cover. Rigor refers to how teachers teach to the standards, and how students show that they understand what is being taught. Rigor can be thought of as a stool with three legs: deep understanding, fluency, and application. Students will need to master all three in order to build a foundation that supports learning. And each leg of the stool represents a corresponding instructional shift. We will explain each of these shifts individually, but let's first define the instructional shift that comes with establishing rigor in the classroom. Rigor is about creating an environment in which each student is expected to learn at high levels. Each student is supported so he or she can learn at high levels, and each student demonstrates learning at that high level. In creating rigorous learning environments, teachers are putting students in the best possible position to develop deep conceptual understanding, fluency, and the ability to apply mathematics to different situations. While each of these concepts relates to the other, each notion will require its own shift to instruction. Let's begin by looking at deep understanding. What do we mean by deep understanding? Students demonstrate a deep conceptual understanding of core math concepts when they can solve short conceptual problems, apply math to new situations, and can speak clearly about their understanding, why they took a certain approach to solving a problem. Getting students to this level is the ultimate goal of the Common Core state standards for math, and will take hard work from both students and teachers. Teachers must make a shift in instruction to emphasize more than just teaching students how to get the answer. Instead, they must support students' ability to access concepts from different perspectives and see math as more than simply a set of mnemonics or discrete procedures. A deeper conceptual understanding must be the goal of instruction. When students can perform mathematical operations with speed and accuracy, they are considered fluent. Math education consultant Beth Kakuza explains how this concept is reflected in the standards themselves.
There are fluencies that are required throughout the standards in every grade, and these are the ones where the word fluent actually appears in the standard. The word fluent was used very sparingly for only moments in time when it was absolutely necessary. And it's also very important to note that these are not, just like we've been talking about the focus and the coherence of things, these are not just plopped in randomly at places where now would be a good time for them to be fluent in this. They're the end point of a progression of understanding. So we're not just saying, all right, let's drop into grade 3 and we're gonna know our multiplication and division facts. That is the end point of grade 3's learning. So there's lots of conceptual development and understanding and discussion and deep thought that's going into developing that fluency, and the fluency is expected by the end of the grade.
So if you're doing something fluently, you're doing it with reasonable pace, good rhythm, not halting or stumbling. It does involve issues of time, and of course accurately. The word fluency also has a larger meaning, though, in math education, as many people point out. Procedural fluency in adding it up is a kind of a big idea that takes into account not just fast and accurate results, but also a strategic component and other things. And the Common Core standards don't mean to redefine that phrase, but in the particular standards in which the word is used, it's a much smaller idea. It just means, can you get the answer reasonably quickly and accurately? Fluency in the balanced way that the Common Core does it is probably a shift for most people, because it asks us to respect both the journey and the end point. The standards make the investments, ask us to make the investments in the conceptual understanding and procedural development of skill from year to year, and applications that make fluency realistic, and then they insist on it. So example of fluent calculation would be, if I say 9 plus 4, and I very quickly say, one more will get me to 10, and then I'm at 13, and I say 13. And I quickly and accurately give you the answer 13, but I've done a little mental process. So that's fluency, and most of the fluency standards ask for that kind of fluent calculation, often mental. You know, for younger kids, there may be some sophisticated strategies that they're using to do it, but it's quick and accurate. Memorize is an even more literal command about teaching. Now, the question is, how do we get to the goal? And the standards are partly designed to make this goal reachable. I like to think about the standards as being a number of trajectories, interpenetrating sometimes trajectories of teaching and learning, so the grades are going up. And we have a pinnacle, sort of, and a pinnacle would be being fluent with the multiplication table and knowing your multiplication single-digit products from memory. But getting there is a bunch of reasoning and practicing and discussing and problem solving, learning new particular ideas that get you along the progression to get there. And there are two mistakes you might make. One mistake is to focus only on the outcome and ignore, this goes from kindergarten all the way up to grade 2, for example, knowing the addition, single-digit additions, single-digit sums. Knowing single-digit sums from memory is in grade 2, but a lot of K2 is building toward that. And so people have to understand that you can't short-circuit that and expect to get good results. On the other hand, another mistake would be to conveniently ignore this because it's sort of a lot of work and feels harsh, and to know single-digit sums from memory is a demand, and the instructional program has to have sufficient strategies to make that work. That is going to include timed practice exercises. It's just, I can't personally, common sense-wise, see how it doesn't include that. But let me just make concrete what I'm saying about the need to not short-circuit things. So when you're in 3rd grade, multiplication, division are introduced in the standards in 3rd grade, and you're teaching a group of children who have no idea what that symbol means, and you're teaching them what that symbol means, and if they so if my math is right, that's 35. Well, in the classroom, a good conversation at the beginning of 3rd grade is, well, why is 7 times 5 35? What does that mean? You're asking them to reason mathematically to a conclusion, so you need to have principles on which you can base your reasoning. And so the principle is in Standard 3OA1, and it says the student should understand a product. M times, 7 times 5 is the number of things in 7 groups of 5 things each. So why is 7 times 35? Well, it's an empirical question, 1, 2, 3, 4, 5. How many dots are there? That's an empirical question. I have 7 groups of 5 things each. How many dots? If I did it right, there's 35 dots. This is called a count-all strategy. And students at the beginning of the year, I don't know what other strategy do they have, but to have a principle and a sort of a definition in mind and to use that definition to reach a conclusion. Later in the year, they'll have more sophisticated strategies. They will understand commutativity, what you get when you flip this up. They will understand associativity and other things. And very importantly, they will begin to understand distributivity, without necessarily calling it that. Let's try a new one. 7. Let's do. Yeah, let's do 7 times 5, but let's think it through this way. The students say, well, I actually remember my 5s pretty well, so I'm going to flip it and think about 5 times 7. And I know everyone knows 5 times 2, right? And 5 times 5 is super easy to remember. That's 25, and that's 10. And this addition is actually quite easy. Right, and the answer is 35. And I could imagine doing that as a very rapid reasoning process. That would be called a fluent calculation of 7 times 5.
This emphasis on students developing procedural skill and fluency provides teachers with an opportunity to rethink how they have structured class time and homework. This is the main instructional shift toward fluency. To develop fluency in procedural skill, teachers are encouraged to structure class and homework times so students spend their time practicing core functions, such as multiplication facts. This way, students are able to understand and manipulate more complex concepts. However, the journey begins with developing that deep conceptual understanding of the process of multiplication. Another aspect of developing a deeper understanding of core concepts and working towards fluency is having students apply specific concepts when appropriate. This is the third leg of our stool, application. Application refers to students using math and choosing the appropriate concept for application, even when they are not prompted to do so. Jason Zimba explains application and how it relates to the guiding principles and instructional shifts of focus and coherence.
Application covers a wide range from simple short word problems with relatively short answers, all the way up to simple short word problems that have very long chains of reasoning and bring modeling to bear, to longer tasks that take a long time to engage with and solve. One thing about focus and coherence that I threw out at the end of a long sentence, which is a bad habit of mine, is that when we focus, we're doing it to allow math instruction to be more coherent. And we're also doing it because we need to have higher expectations for those things. And that's going to require tactically some intensity. So conceptual understanding requires intensity of a certain kind. It requires thinking hard.
Just as with the other legs of our stool, application invites educators to make an instructional shift so that students gradually grow in their ability to identify the appropriate concept for application. Teachers can shift instruction to consciously provide more opportunities at all grade levels for students to apply math concepts in real-world situations. This also has implications for teachers outside of the content area of mathematics. Science teachers, for example, can also work to ensure that students are using math to make meaning of content and to access material. Let's now look at an example of how word problems can be constructed so that they provide students an opportunity to identify the appropriate application. In this problem, students are asked to think through the algebraic equation required to find the solution. That equation becomes x is equal to 3/4 x plus 3/4. Having to think through the wording of a problem and apply algebraic thinking is a prime example of application. Thinking through the application and working hard to find the answers requires some intensity, another concept Jason alluded to. In order for students to benefit from a rigorous learning environment, instructional shifts must be made to push them towards developing a deeper understanding, fluency, and a mastery of application. The Common Core math standards invite practitioners to adopt strategies that help students meet higher goals. They also invite teachers to spend more time deeply covering and focusing on topics and challenging students with well-constructed problems. In order to be successful, our students need to master key mathematical concepts by applying them to new situations and do more than just learn how to arrive at the correct answer to a problem. By incorporating these principles into our work with the math standards, we will be building a platform or stool from which students can reach higher and achieve more. Through this video, we have walked through each of the guiding principles and instructional shifts within the Common Core State Standards for mathematics. To quickly recap what we have covered, we first took a look at the principle and instructional shift of focus, and how an increase in focus means that we'll need to spend class time focusing where the standards focus, on core concepts and how they relate to each other. We also discussed paying attention to how the standards coherently link concepts, both within and across grades. We then explored the aspects of a rigorous learning environment, where instead of just trying to help students get the answer to problems, the goal was to push them towards a deeper understanding, where students are fluent in their calculations